Okay. Hi, everyone. Welcome to the 46th session of our MedAI group exchange sessions. This week, we have Laura Manduchi from ETH Zurich here with us to present her research on incorporating domain knowledge in deep generative models for weakly supervised clustering. Laura is a PhD student in computer science at the Institute of Machine Learning at ETH Zurich under the supervision of Julia Watt and Gunnar Ratz. I'm sure I'm probably butchering their names, but please feel free to look it up as well. She's also a member of the Medical Data Science Group and the ETH AI Center. Her research lies at the interplay between probabilistic modeling and deep learning and focuses more on representation learning, deep generative models, and clustering algorithms. She's particularly interested in incorporating domain knowledge in the form of constraints and probabilistic relationships to obtain preferred representations of data that are robust to biases with applications in both medical imaging as well as X-ray astronomy. So thanks so much for Laura for joining us today. And before we actually get started, do you have any preferences on how you'd like to take questions? Would you prefer them at the end or during the talk?
I actually don't mind. So whatever you prefer, it's fine. Also, I have two works that I will be presenting, so maybe I can take questions after the first work and then the other set of questions after the second, if that's easier.
Okay, awesome. That sounds good. And so, as always, let's try to make this session as interactive as possible. And without further ado, let me hand it over to Laura. Thanks, Laura.
Thank you very much for the presentations, and then thank you also for having me here or there, actually. So I will start by sharing my screen. And maybe you can just tell me whether you can see it in the presentation mode. Perfect. Okay, so as already been introduced, and today I would like to talk about how to incorporate prior information given by practitioners, given that we are given the experience in the medical domain, into deep generative models. And deep generative models connects basically neural networks with probabilistic graphical models. And the reasons why I'm focusing on deep generative models, as we will see, is that it's because they specify clear and interpretable assumptions underlying the data that we process. And so throughout this talk, I will mainly focus on the application of weakly supervised clustering. And before I dive into the topic, maybe I can take a few seconds to be sure that we know what we're talking about, especially in the context of deep clustering. So as you might all know, in clustering, we have a dataset X that we wish to cluster. And in the classical clustering scenario, we cluster the data in the raw input space. Now, this has been shown to not perform really great, especially when the data modality is rather complex. And for example, when we're dealing with high dimensional data, that could be videos, that could be images, for example. And so instead of actually clustering in the raw space, what we do, we cluster a latent representation of the data. And so the clustering basically entails all the clustering methods that exploit the flexibility of deep neural networks by clustering a latent representation that has been obtained through deep neural networks. And deep clustering has recently become a major trend in machine learning with an abundance of new approaches every year. And they do show a striking performance on real-world data. Unfortunately, in medical application, it's often the case that these completely unsupervised approaches actually are quite limited in medical application. And here I would like to stress that clustering is an unsupervised approach. So I know that calling it unsupervised deep clustering seems a little bit redundant, but I just wanted to make sure that with these classical clustering methods, we are not using any metadata or any additional side information that is not contained in X. And so we encountered the limitation of this unsupervised approach while exploring different medical data sets. Here, for example, we explored a data set of newborn echocardiograms that we will also see in the second application, which are ultrasounds of the heart. And here, the doctors were interested in exploring how the data cluster according to different clinical characteristics. And we try out different clustering algorithms and we try to see how the clustering performs on different clinical variables. And here, for example, I plot how one state-of-the-art, at least it was state-of-the-art 2 years ago, how these clustering methods perform on premature birth category, which is basically indicates how premature the newborn was born. And as you can see here, we can retrieve some blobs of clusters, but in practice, if we look at the accuracy is quite low. And so the problem is that with unsupervised clustering algorithms, we might find solutions that are not consistent with the domain knowledge. And that's because the algorithms might pick up biases such as the type of machines used to record the data or other information that might be critical for the data itself, but they're not important for the clinicians or for the particular application. And also what we observed is that it's often the case that practitioners do have some prior information about the clusters that are sorting the data. So what we asked ourselves was how to incorporate such domain knowledge and how to define a principal method that could drive the clustering algorithm toward a desirable partition of the data. And so we enter here the regime of weakly supervised clustering. I know that might sound confusing because you might have heard about weakly supervised learning. So now I'll try to explain to you the difference. So the main concept is the same. We don't have access to ground truth label. And the difference with weakly supervised learning is that we actually, in clustering, we are interested in discover clusters in the data. So we are not, we don't really know what we are looking for from the very beginning, but we do have some kind of weak form of supervision. And usually this weak form of supervision, it's incomplete. That means that we don't have information about all the data points, but also it's inaccurate because it could contain quite a noise, for example, especially in the crowdsourcing scenario where we have a lot of annotators that are not domain experts. But most importantly, they are inexact. So that's, I think, the most important bit about weakly supervised clustering. We don't have the knowledge about the cluster assignments, and we don't have the knowledge about the labels. What we do have, we might have some side information that give us direction towards the correct clustering algorithm. And so in this talk, I would like to explain two of the most recent work that I've done in the past 3 years. And the first one was how to incorporate survival data into the clustering algorithm to drive the process into the desired partition of the data. And the second one was how to integrate a different type of set information, which is instance level constraints or pairwise constraints, where we assume that we have some annotators that look at some pairs of data and basically tell us whether these pair of data look similar or not, according to the domain knowledge. So I will start. Actually, it's important here that both works are based on weak supervision that are incomplete, inaccurate, and inexact at the same time. So I will start with the first work. This is a joint work with Richard Markinovich, and we work together with other collaborators from the medical domain and from the technical domain. And before I dive into the method itself, maybe we could have a look at survival clustering as its basis of our method. And in survival clustering, what we try to do, we try to infer a function between inputs X and time to event. And the time to event could be time to any adverse events like death, that's the most common one, or cancer recurrence or rehospitalization, and so on and so forth. And the problem in survival analysis is that these time to event might be censored. So that means that we don't observe the complete information about these time to events, But for specific patients, we might have partially observed information. So what does it mean? It means that the patients could withdraw from the study. For example, I don't know whether you can see my arrow, I hope yes, but maybe we can see these patients here. So these patients, after 1,000 days, decided to drop from the study. And so we don't have the information of what happened after these 1,000 days. So we know that these patients survived for 1,000 days, but we don't know when the event happened. And that means this patient is censored. And there are a lot of different reasons why a patient could be censored. It could be that the study finishes. It could be that they decided to drop the study, and there are other reasons as well. So given this censoring data, this task is rather difficult. Well, yes, challenging, but also it's different from the classical regression models. And so if we put it a little bit more formally, then we have a data set with the time to event that could be censored. And then we seek to find this survival distribution. So the probability of survival, that means that the event does not occur over time. And then the challenges, as I said, is that the data is censoring, but also the challenges is that here the data could be highly unstructured. So it could be videos, could be images, could be whatever. And that means that we have this highly nonlinear and very complex relationship between the data and the time to event. And it could be that it's also impossible to retrieve such function. Now, in this work, we are particularly interested in survival clustering. So that means that instead of just modeling one function for the complete set of patients, we want to discover subgroups that are characterized by different survival models. So again, given the data, the goal of survival cluster analysis is to first discover the cluster assignments for each patient, and then condition on these cluster assignments. Then we would like to find the survival distribution. So the survival distribution is conditioned not only on X, so it's a function that takes as input not only X, but also the cluster assignment. And as you can see, the difference with survival analysis is that in survival analysis, we have one function that characterizes the entire population. And why we're interested in survival cluster analysis? Well, because we would like to find different types of disease or disease subtypes that are characterized by different survival models. And so we are in the regime, again, of weakly supervised clustering or learning, as we would like to call it, because we do have additional side information in the form of survival time, which is partly observed. So it's also inexact and could be noisy, of course. And the side information, so the survival time, it's something that also we would like to predict at test time. So we don't have it available at test time. So maybe we could look at a practical example to make things easier. So we have this pool of patients that we would like to cluster into different groups. Let's assume that here we have 3 different groups. And these patients are characterized by different features that could be age, treatments, information, lab results, and we have the time to event that could be censored. And the idea is that all these groups are characterized by different associations between the covariates, so the input X and the survival time. And we can see here, for example, that group 2 is characterized by a higher survival probability, while group 1 and group 3 are characterized by a similar but lower survival probability. So one might think, why should we have group 1 and group 3, given that they have similar survival probability? Should we just merge them? But if you look into the importance that these different features have for the survival probability, you can see that, for example, in group 1, treatment B is crucial for the survival of the patients, while for group 3, treatment A is more important. So with this example, I just wanted to highlight the fact that in survival clustering, we don't want to stratify the patients only by their survival risk, but also by their different phenotypes, because ultimately we would like to have a more personalized disease management. And so what happened at test time? Well, we have a new pool of patients that come in, we train the model, we don't have the survival information, something I would like to to discover. And so we cluster the data according to the input X, given the trained model, then we condition on the cluster assignments, and then we can predict the time to event. So we kind of have two tasks in this model. Before we want to cluster the data, and we also want to predict the time to event. So maybe here is a little bit redundant, but I just wanted to make sure the importance that you understand the importance of such model. But the idea is that we would like to do exploratory analysis for complex survival data. And we would like to perform subgroup analysis to have a better understanding of diseases and their progression. And of course, we want to have a flexible survival analysis that could take in different data modalities. And so for this, we propose variational deep survival clustering, which is based on a variation autoencoder with a Gaussian mixture prior in the latent space. To perform clustering, this is also called variation deep clustering in the latent space of variation autoencoder. But that's not enough, because we also want the clusters to be informed by the survival time. And for this, we model cluster-specific survival distributions that are, again, defined in the embedding space. And these are modeled by Weibull distributions with cluster-specific scales. So we have a mixture of Weibull distributions. Each Weibull distribution is assigned to one cluster. And so maybe we could have a look at the generative process of the data, so the assumptions that we make. And what we assume is that we can sample a cluster with a categorical distribution. Then we can sample the latent embeddings that are conditioned on the cluster assignment. So here, the latent embedding, as I said, is a mixture of Gaussian. So we can see here it is a Gaussian with mean and variance sets dependent on the selected clusters. And then given Z, we can sample the input. And this is basically similar to a variation autoencoder. This, again, could be a Gaussian or a Bernoulli, and the mean and variance are the outputs of the decoder. And then on top of it, we can sample the time to event probability that are conditioned on both the cluster assignments and the latent embeddings. And then the question is, how can we, now that we define this generative process, how can we optimize it? So how can we find the parameters of these distributions that describes the data better? And for these, we derive lower bounds of the log likelihood, similarly to a variation autoencoder, but with these different distributions. And then we optimize it with the batches and stochastic gradient descent. And of course, we also use all the tricks that are used in variation autoencoders, such as Monte Carlo sampling, and so on. And now we can directly look at some, I haven't put the math here because if you're interested in, of course, you can look at papers, and I will put the QR code at the end. But maybe we could have a look at
Can I ask a question here?
Yeah, sure.
About the, so you assume the time to event is coming from a Weibull distribution, is it? Why exactly? Why do you choose that particular distribution?
Yeah, that's a good question. So we first of all, we studied different distributions that were out there. So we were also thinking about the Cox mixture distribution, but that is a semi-parametric model. So at the end, we decided the Weibull distribution based on related work mainly, and also because it's a fully parametric model, and so that was fitting in nicely. And also because at the end of the story, we observed that the Weibull distribution was already giving the best performances. So we didn't explore too much in that direction, although that could be a future work that we could do, definitely.
Got it. Thanks.
Okay.
Actually, a follow-up question on that. Could you not sample the like time to events directly from your training data? Like, why would you need to assume a distribution and then sample from that? So
the idea that we sample from it because here basically I'm describing the data generative assumptions, and maybe it was a little bit confusing when I say we sample from. It's just in my way of thinking. When I define a new problem in the deep generative model scenario, I always first try to think what the assumptions of the model. So this is like, if I want to create new inputs, if I want to generate new inputs, what should I do? Well, first I sample a cluster, then I sample Z, then I sample X, and then I sample T. So that's how, and this is basically used to define the log likelihoods. And we do that such that we can fit the parameters of this Weibull distribution. And if we fit the parameters of the Weibull distribution, now if we go back at test time, so here, is it? Yeah, here, let's see. If we go back at test time, then if we know the parameters of that characterizes the Weibull distributions, that we are able to predict time to event. So that's the reason why we sample time to event, because we want to learn it, because at test time, we don't have this information available. And even at training time, we have it partially observed, because many patients are censored. So we don't have that information for all the patients. So we want to learn the parametric model and the parameters that characterize it in order to infer this time to event at test time.
Gotcha. Okay, thank you.
Yeah, thank you very much for the questions, and please ask me if it's not clear. It might be that for some certain parts I'm going too fast and others I'm going too slow. But anyway, we can look here at one synthetic experiment that we performed. And here we use survival MNIST as a data set. Survival MNIST, it's rather simple. We have MNIST and then we associate survival distribution to different subgroup of digits randomly. And here is the ground truth survival distribution. So we have the survival probability over time. This is what we create in the synthetic data set. So we have 5 different clusters, and we can see that cluster 2 and 3 have a similar survival distribution. Actually, it's almost identical, but these are characterized by different digits. And same goes for cluster 4 and 5. Now we can look at certain baselines. So we train a variation autoencoder plus a Weibull distribution on top, so not end-to-end. We can see that the clustering performs rather good, but then it completely messed up with the survival distribution. So the takeaway message here is that we need an end-to-end training technique in order to infer the right survival distributions. Otherwise, the variation autoencoder will just basically discard all the survival information. Then we also have survival clustering analysis, another baseline, and we can see that it fails to retrieve 2 clusters that were quite similar. And same goes for deep survival machine, where basically on the other side, deep survival machine completely discard the information of digits, and it's just informed by the survival time and tries to maximize the difference between the survival times of the clusters. So it only predicts the survival risk. And then the proposed model, it's nice middle ground where we can retrieve the clusters, and we can also retrieve the correct survival probabilities. And maybe more interestingly, we also perform experiments on a real-world data set using non-small cell lung cancer data sets, where we collected a set of data sets of computed tomography images from these non-small cell lung cancer patients. And we use our in-house based data set from Basel. We also use some data from the Netherlands and some from Stanford University. And this is, of course, we had to work quite a lot on pre-processing the data. This is like one example of a CT slice. And actually, these data, it's in the form of 3D scans, but for simplicity, we only retrieve 2D scans out of it. And then we can have a look at the predictive performance in terms of...
Sorry, Laura, I just have one quick question.
Sure.
So how did you define the number of clusters here?
Yeah, that's a good question. The number of clusters is something that we have to give a priori. So we are actually working, we would like to work on a Dirichlet process in order to not give that a priori, such that the model can learn it. And here we just try out different number of clusters. So the higher number of clusters, the more refined characteristics, but of course there is a trade-off.
Right,
so
because I would imagine, like, since you have these 4 groups where 2 groups has like very similar survival probability, or survival estimate, probably you can even go with 3, right? But in that case, you lose that information that you want to capture, that precision medicine kind of line, that even if they have like similar survival, but their features are slightly different.
Exactly. So that's a very good point. So just to make clear, though, this one is a synthetic data set. So these survival distributions are not connected to these other real world data sets. But this is a very good point because what we want to do, we don't just want to predict the risk. So we don't want to have cluster completely characterized by the survival distribution.
Exactly.
We want to also model the phenotype of the disease. So we want to take both informations into account for clustering. So that's exactly our goal. So you describe it very well.
I actually have a follow-up question. So currently, this method, you need to define a cluster a priori. Then how do you pick the number of clusters in the end? Do you look into the clusters and see which one makes more sense based on domain knowledge, or?
Yes. So we assume that we do have some domain knowledge. Now the rule of thumb is to actually don't exceed 10 clusters, because then it becomes rather difficult to find informations out of it, depending on the application. So I think it's more it's based on domain knowledge. So how many clusters the clinicians are looking for in the data. But what we do in practice, we try out different number of clusters and look at the results and look at how the survival distributions are different from each other's, and whether we could see by generating the images, whether, since we're working with the images, whether we could see different meaningful differences in the different clusters. And then we kind of there are different scores that one could use. There is the big score and others for which one could automatically choose the number of clusters. So there is a trade-off, between performance and complexity. Here in these experiments, we just try out with a few different number of clusters, and we didn't really explore too much in the number of clusters because, as you will see, for example, in this real world data set, actually these are the predictive performance, but here we chose 4 number of clusters because if we were choosing more, then it was very difficult to explore the results and explain them. But I think it's a downside of this method. So one way to overcome this problem is by using non-parametric priors. So Dirichlet prior is the most commonly used. The problem with these non-parametric priors that they basically decide number of clusters with Bayesian theory, they are quite unstable. So in clinical applications, having this Dirichlet prior doesn't really help too much, because then you really have unstable results with different runs, and that's not exactly what we want.
Thank you.
Okay. So this slide is just about the predictive performance. So how good we are at predicting survival time at test time. And this is like the strongest baseline that we decided to retrain deep survival machines. And we can see that we perform quite good and in par with the traditional radiomics-based approach. So in radiomics features, we take into account the pixel-wise tumor segmentation. So this is like an upper bound of the performances, because they do have information that we don't have. So this tumor segmentation is something that we don't use for these 2 methods, but it's used for radiomics together with other features. And then more interestingly, we can look at the survival distributions that we discover in these data sets. And we can see that we discover one cluster. Sorry, my window. Okay, now it should be fine. So we discover 4 different clusters, meaning the number of clusters set a priori, as I said, but we can see that they have rather different survival distributions, especially between cluster 1 and cluster 4. And if we investigate how the generated CT scans look like for these different clusters, we can see that the cluster with the higher survival probability actually contains tumor that are mostly located in the upper lungs, while the ones with the lower survival probability, then it's contains clusters in the lower lungs. And this was quite an interesting finding because it is actually confirmed by medical research, where they state that the tumors located in the lower lungs have a lower survival probability.
So you're directly using the 3D images, or you are using the 2D selected plane?
We are using the 2D CT scans. So we didn't use 3D because of time, although now we are working on extending it to 3D, because of course, by just using 2D, we don't have the full information. So we are really reducing the information quite a lot. So
also you are depending on somebody to select you the slides, right? Where you have to see the tumor.
Yes, exactly. That's another downside, because that's an information that we had in the data set where the tumor was located, and different baselines were using like location, and then it was taking, of course, a random CT slides. But the problem with these CT slides, sometimes they have like slides in the brain that they don't really fit that much with this application. So we had to use this information, but then of course we selected the slides a little bit randomly within a range. But the idea is that if we go for 3D, then we don't have that problem anymore. And in theory, you know, it's possible. We just have to modify the encoder and decoder structure. And then, so we could look at the generated samples. So from our model. So here are the means of the 4 clusters that we generate. And then here we can see the counterparts of the baseline, and we can see that in the baseline, given that this is completely risk-driven, that means outcome-driven, so it's only looking at survival time and not at different features, it doesn't pick up, especially if we plot the assigned samples, we can see that for the baseline, it doesn't really pick up any tumor location. While our method, given that it clusters also according to the phenotypes and according to the features of the raw input, then we can also pick up not only different survival distributions, but also different tumor locations. And of course, we investigated other different clinical variables, such as age, tumor volumes, and so on. And we observed that there was substantial differences between the different clusters. So we can see that cluster 1 with the highest survival probability has, for example, a smaller tumor volume than cluster 4, and also a lower mean age. And same goes for the cluster with the lower survival distribution. So maybe I should start going a little bit faster. But basically, the summary of this first part of the talk is that we focus on outcome and covariate-driven clustering, as we discussed before. So we were not only interested in survival information, but also in disease phenotypes. And for this, we defined this deep probabilistic model that have different genetic assumptions to previous work and improve clustering performances, and was competitive at time-to-event modeling. So at the end, we kind of find this holistic representation learning view of survival data, and we apply it to medical imaging data. And if you're interested, of course, here is the QR of the paper if you want to read more about it. And this paper has a very huge appendix, so you will not get bored in reading about it. And now we can quickly talk about the second work, unless you have any more questions.
Maybe you can go with the second work and then we can ask questions together.
Okay. Yeah, perfect. So for the second work, Basically, here we were interested, instead of inputting study information in the form of survival time, we wanted to look at distance level constraints. So this is I performed this work together with my collaborators, so Kieran from the machine learning domain, Holger and Sven from the medical domain, and Julia Vogt, my supervisor. And maybe I can start with quickly describing what is constraint clustering. And constraint clustering, basically, as I said, incorporates existing knowledge in the form of instance level constraints. And what are these instance level constraints? Well, basically, instance level constraints tell us which samples should belong to the same clusters and which not. So we assume that we have a pool of annotators that look at some pair of images, not all, of course, a very small subset, and they see whether the images or the data look similar, then they assign a mask link. So the data should be clustered together. If they are dissimilar, then they should assign a cannot link. Why am I interested in constraint clustering? Why do I want to input this weak form of supervision? Well, first of all, because it requires milder assumptions, and there is no need to define classes. And it's, of course, if you're looking at just images of cats and dogs, defining classes is not very difficult, but there are certain type of data sets, for example, the one containing different breeds of dogs, where there are around 120 different breeds. So actually defining classes is quite cumbersome. And then, of course, comparing, it's easier than labeling. So that's the ideal setting for a crowdsourcing scenario, because we don't need domain experts to just compare images. And then lastly, if we do have some labels, we can always convert them into instance level constraints, but we cannot do the opposite, because instance level constraints do not contain information needed to actually derive the labels. So that's why it's a weaker form of supervisions.
Quick question here. So similarity, the notion of similarity can be pretty broad. Like, for instance, two dogs of the same breed are definitely more similar than two dogs of different breeds, but they're definitely similar compared to a cat and a dog. So do you care about those kinds of like if you're given two dogs of different breeds, would you assign a must link or would you assign a cannot link in this category?
So I think that's a great question, because that's exactly the problem of unsupervised clustering, right? So in unsupervised clustering, you could cluster according to cats and dogs, or you can cluster according to breeds. And that's exactly described by the domain knowledge. So according to the domain knowledge of the annotators, then they have different concepts of similarities. So they encode their the applications that they're aiming at by different measures of similarities. So if we select annotators that are interested in breeds of dogs, then they will assign similarity according to that. Mm-hmm. So and it's very, yeah.
So there is a consistency amongst annotators. So there is no noise between.
Yes, although as I will show later, different annotators may have different noise levels. So we are not assuming that the annotators are always correct. So we are giving some flexibility in the model because of that. But yeah, the idea is that you select a set of annotators from one domain.
Got it. Okay, thank you.
And so in this work, basically to approach this constraint clustering problem, we propose the conditional and Gaussian mixture model that uncovers in a similar fashion as I described before for the survival problem. We want to uncover the data distribution, but this time we condition on these instance level constraints that have different degree of certainty, so different noise level, let's say. And as before, we would like to have these interpretable, intuitive, generative assumptions, as I will explain to you in a couple of slides. And of course, as in all deep learning techniques, we would like it to be trained efficiently. And so, if we look at the Generality model, this time, what we have a dataset X that again we wish to cluster into K groups, but this time we have prior information W that is given. And this W is a matrix It's a very sparse matrix with n columns, n is the number of samples. So we have n columns, n rows, and we have mostly 0 entries. But for certain pairs that where we observe some instance level annotations, then we can input an entry. And so this matrix basically encodes all the different constraints that we observe in the data set. And so what we do, we condition the cluster assignments on this W, on this matrix. And then given the cluster assignments, and again, we can sample the latent embeddings that again follows a Gaussian mixture model. And given the latent embedding, we can sample the row input X, again, from Gaussian with mean or Bernoulli, depending on the data, with the parameters of this model that are the output of the decoder. But differently from before, this prior probability, so this P of the cluster assignment given our prior information, it's not independent among samples. So we cannot compute this as a product over the different cluster assignments. So the math behind it is a little bit more complex. We have to use different tricks, and for that I refer to the paper. But the main concept here is that the data here are not independent and identically distributed anymore as in the classical variation encoder, because we condition, given that these are pairwise constraints, we have to condition the labels to the rest of the data set, because maybe that sample need to be clustered with sample 2 and sample 3, so we need to look at the entire data set in order to see the different instance level constraints. And given that I'm running out of time, I might skip this slide. It's just like the insight of our conditional prior probability, which basically use a weighting function. And this is just, here I just explain how we can select the entries. So the idea is that if we observe a mass link, then we put a positive entry in our matrix W. If we observe a cannot link, then we put a negative entries. If we don't observe any information at all, which is most of the cases, then we have a 0 entry. So this matrix is very sparse, 99% of the data, it's 0. And then the magnitude of these entries depend on the degree of confidence of the annotators. And as before, we would like to optimize the log likelihood, and for that we derived a lower bound. And the lower bound consists of 2 terms. The first one is the reconstruction term, as in the classical variation encoder. The second one is the Kuba-Leber divergence between the probability of the latent embeddings and the latent cluster assignments and the conditional Gaussian mixture model. So what it means that we enforce the latent embeddings of the variation encoder to follow a Gaussian mixture distribution that has to agree with our clustering preferences. And then as before, we can approximate it using SGPB estimator, and the computation complexity scales quadratically with the batch size, not with the data size. That's a very important point because we want to train it efficiently. And here we can quickly look at the results. And most importantly, we use different data sets, so MNIST, special MNIST, reuters, STL10, so pretty basic ones. We also have results of real-world scenarios, as I will show it to you in a couple of slides. But we just wanted to see whether we could improve performances from the unsupervised counterparts. This is completely unsupervised. And then we can see that we achieve higher performances also compared to the rest of the baselines. Here we put the state-of-the-art of constraint clustering that it's out there. And we can see that we actually achieve state-of-the-art constraint clustering performances on these different data sets. And here we use 6,000 instance level constraints, and 6,000 instance level constraints can be derived from around 100 labels, because you can always transform labels to instance level constraints, but not the opposite. And this is actually a very small ratio of the entire pair of instance levels pairs that you can have in a data set. This is like the total number of pairs in a data set is something like n to the power 2 minus something, of course, but so 6,000 out in a data set of 70,000 is actually a very low number. And then we also found out that this constraint IDEC was the strongest baseline, so we we start investigating what were the differences between these two methods with different settings. So here we varied the number of distance level constraints. We could see that our model performed even better with a smaller amount of distance level constraints. So it could really pick up information with even a small number of constraints. And also we test out a noisy setting. So we assume that we have annotators with different noise levels. And we can see that the higher the noise level of the annotators, actually the more difference the performances of the two methods. And our method is the one with the higher accuracy here. And then we also apply our model on two real-world applications. The first one is by using a dataset of infant echocardiogram videos. And here we wanted to test our approach on two different clustering settings. So in the first one, we try to cluster according to the view of the echo, so the angles of the echo. And the other one is the preterm information, so how young the newborn was born. And the first result is that we admit a degree of control in choosing the different clustering structure. So we can see that we achieve quite good results. Preterm is a rather difficult problem, but we could see that we could change the clustering structure if we input different type of information. But most importantly, if we look at the results of the complete unsupervised approach, they are definitely lower than our method. So it's the inclusion, as I was telling you at the very beginning of this presentation, we believe that the inclusion of this domain knowledge is actually very effective for medical purposes. We can see a very big boost in performances compared to the unsupervised approach. And then we also try out using the UTK phase dataset. And here we can see the results of the unsupervised method for genders. And as soon as we input information given by 1.5% of the total labels, we can see an each division of clusters in the latent space. And same goes for ethnicity. So again, we show a remarkable improvement with the inclusion of these distance level constraints. So we can finally go to the summary, and here we propose this method that has these intuitive assumptions on the data generative process and uncovers the underlying data distribution. And empirically, we could demonstrate that we can indeed drive the clustering toward different partitions, and it's quite robust to different type of noisy constraints, and also it's quite good in performances. So to conclude, the takeaway messages from these two works that are presented today, we explored weak supervisions in variation deep clustering setting using pairwise constraints and using partially observable outcome variables. And we use this interplay between neural networks and probabilistic graphical models. And we did that because we want to derive a loss function from the likelihood rather than actually have heuristic losses, which are always cumbersome to tune because you have a lot of hyperparameters. And the good thing about these two works is that you basically don't have much upper parameters. You have to select the number of clusters, but you don't have to fine tune other hyperparameters. And then we show that in these different medical applications, leveraging domain knowledge is crucial to overcome the limitation of completely unsupervised approaches. So if we do have some set information, of course, it's better to give it an input. So we don't need the full labels in a clustering to drive the clustering setting. And of course, our ultimate goal was to do exploratory analysis with complex data type. And with that, I conclude. I went a little bit over time, I'm sorry for that. But if you have any more questions, I will be happy to answer them.
Yeah, thanks, Laura. That was a great talk. Maybe before we start the questions, we can all give a round of virtual applause to Laura.
Thank you.
Yeah, that was very well explained and very cool concept as well. So folks who have questions, we can get started.
May I know your insights about using your first work, clustering method, survival clustering method to discover, say, like which patients would benefit more from one treatment versus another?
Yes. So, sorry, can you, the question was, what's the insight?
Yeah, what's your insight? Like, do you think, or have you done some experiments on this?
So, and that's a good question. That's our ultimate goal. Unfortunately, in research, we always have to, in order to find medical relevant finding that could be actually applied in practice, we have to go through an endless series of validation with the clinicians. We didn't have the time to perform that. But here, I think the most important clinical finding that we found and was confirmed by literature is that the tumor that is located in the lower part of the lungs have a lower survival distribution than the tumor located in the upper part. So that was one finding that we could double check with related research work. Now, we didn't take into account, so in this data set, we only use the CT scans. We didn't use the information of treatments. And I think if we use information of treatments, we could really obtain better results. But here we only use CT scans for simplicity.
I see.
And at the moment we are working on extending such work by using 3D scans and using also treatment informations and other metadata as well with the survival data in order to find more clinically relevant information. And so we would like to maybe aim for a journal for this, because this was published at the iClear conference. So we have a limited amount. We have 8 pages or like 40 pages of appendix. Maybe, if we aim for a journal after this, more maybe targeted toward the clinical domain, that we can really explore the additional finding, maybe also use different data sets as well.
Great. Looking forward to it.
Thank you.
So Laura, I have some quick, sorry, Nandita, you want to go? Go ahead.
Oh, no, you can go ahead, Iman. I can ask my question after that.
Okay. So Laura, so I have just like some doubts here, because since you mentioned that you are also considering that how to include the treatment information, patient demographics, or any other kind of like variables with this. But don't you think that like, since you are putting kind of like generative model in the same space, given like these data are coming and this data ranges varies a lot, and you cannot really do the normal normalization of the images and this data together, that may affect your model performance too?
Yes, so one should go for the multimodal variation autoencoder in that sense. So my plan, it's not to just smash everything together in one vector, because I think that would definitely not work. Our direction that we have in mind at the moment is to extend this work in a multimodality setting. So there has been some work there, in I think it's called multimodal variation.
Right, multivariation and encoder,
yeah.
But I believe, like, since you are still working with the raw data and you still have a strong input for generating the reference, but if you mix this kind of like categorical variable, everything together, even if with multimodal representation learning, but since they are not really like proper data, there is a lot of noise there and there's a lot of variation there, that would also be like a lot of effective for your models, though it may give you some additional insight.
Yes, I do agree that it might degrade the performance, especially if we input data that are not relevant. Although I have to say that even for these CT scans, there was a lot of noise, to be honest, because they really come from different positions. And sometimes there was even no tumor inside. And there was a lot of variability for that. We have to use a lot of argumentations, a lot of tricks to make it work. So even these CT scans are quite noisy, I have to say. But I do agree with you that one should input data with care. And but I also do believe that there are a lot of relevant information. So I think I wrote them here that are not captured by CT scan, such as radiotherapy, such as other treatments information. Age, for example, is crucial. So I think by inputting these different metadata, one could achieve better performances, although it's true that one needs to take care of these different data modalities in order to not degrade the representation of the data.
Okay, makes sense. Yeah, Anita, go ahead. Go ahead.
Oh, sure. So I found this concept of like driving the clustering in a certain direction to be very cool. But I had a question on like expanding it a little further. So in the first case, you wanted to use both the disease phenotype as well as a particular thing that you had observed, which is the survival analysis to actually cluster. And in the second, you used that like basically annotators could choose one direction for determining similarity. So I was kind of wondering if you could expand this into, let's say, as a domain knowledge expert, you know that, okay, I want these subclusters based on many different things. Like I want age, race, like demographics, as well as phenotypes. Like, would it be possible to just keep adding more and more such directions within the same framework, or would the framework not really allow you to have so many different conflating variables?
Yeah, that's a very good point. At the moment, I think adding site information like age, for example, I think there must be some work out there. I think it's a maybe simpler scenario. So here, for this work, so for the constraint clustering, we looked at pairwise constraints because we found that in the literature, pairwise constraints were underrepresented, and it was the methods out there were not very convincing. And it's a difficult problem because, as I said, the data are not IID. And then on the contrary, with this work here, we use survival data. So we use Weibull distributions. We can't use Weibull distribution for age. So I would say that actually that's a downside of these two methods. They are really targeted toward either survival data or pairwise constraints. So if we want to add different site information, then we would need to modify it. I think that maybe one could easily modify this approach. So if we go to the data generative model, so the only difference here would be that T is not a Weibull distribution, but is another distribution. But one needs to change this distribution. So I would say that it could be generalizable, but needs some tweaking.
Gotcha.
But I think it would be cool to have like this model that could work for any site information. I think that would be like the ultimate goal there. But,
yeah.
We're a little bit far.
Yeah, but I also think that for survival data is very unique time to event. So even if there's a generic model that can work for other types of like continuous or categorical variables, it may not work for survival data, right?
Exactly.
I guess you might need to like add an additional variable here to take into account of other types of variables other than time to event.
Yeah, because survival analysis is very different from regression, as you have these partially unobserved variables. It's very unique, as you said. So one need to modify it, of course.
Oh, and one other follow-up suggestion or idea, I guess, is in the second part of your talk, where you talked about this pairwise similarity. If we could also input a notion of, like, you had this confidence of the annotator as an input, but instead of that, you can say, okay, X is similar to Y, but X is more similar to Z rather than Y. So this concept of like the distance of similarity, if you could input that somehow, I think that would be very cool in medical applications, because folks, like even doctors, when they look at two CT images, like it's hard to say if they're similar or not, if even if the task is quite well defined, because there could be so many notions of similarity. And so having three things and then saying, okay, one is more similar than the other could actually make that a little more targeted.
Yeah, I completely agree with you. I think this would be a very cool research direction. And honestly, I haven't still thought about it, but thanks for the input. I think in general, I have seen some works definitely last year in Europe, it was 2 papers were there about this comparison, like what is similar to what, what's more similar to what, this is more similar, so Y is more similar than X, and whatever is less similar. I think this is very interesting, and I think there is a way for kind of integrating such information in this deep generality model, but something that I haven't worked on, but I do agree it's a very interesting future direction that one could take into account. I also think it's very important for the clinical applications.
Awesome. Maybe we are slightly running over time. So are there any last questions that we can ask Laura? Or if not, we can, maybe I'll just pause for a second to ask if there are more questions. Okay, so if not, maybe we can all thank Laura again, and we'll put up the YouTube video soon later tonight. And then if you have more questions, we can all reach out to Laura directly as well. So thanks again, Laura. Great talk.
Thank you very much for all the amazing questions.
Thank you, Laura.
For having me here.